Alright, sports fans, let's watch another video on DNA. We're getting close to the end. We've only got a couple more to go. Today, what I want to talk about is, is the structure of DNA. So we got really, we kind of got some hints in our last video about the structure of DNA. And if you remember, we had these nitrogenous bases: adenine, guanine, cytosine, and thymine. Remember, uracil is only with RNA. So here's our bases. And what Chargaff taught us, Erwin Chargaff said that adenine only bonds with, well, it's not even that it only bonds. He didn't say that. He didn't know that. What he knew was that there was the same amount of adenine as there is thymine. That's what he realized. Same amount, same amount. So if there's 10 pounds of adenine, which of course is a giant amount, there's not 10 pounds, but if there was 10 pounds of adenine, there'd be 10 pounds of thymine. And if there were 10 pounds of guanine, then there are 10 pounds of cytosine. In reality, we're talking like micrograms of adenine and micrograms of thymine, but the point is, it's the same, okay? But adenine is not the same amount as there is cytosine, and guanine does not have the same amount as thymine. That's what Mr. Chargaff said, and so that's kind of something that we've learned from that. Okay. Well, so where's that leave us? All right, so they knew that about DNA. And they knew DNA had some sugar in it with the deoxyribose, because DNA stands for deoxyribonucleic acid, which maybe I should type that up for you. There you go. Let's make it bigger. Deoxyribonucleic acid. Okay, maybe let's put it right there. That'll work. Deoxyribonucleic acid. That's what we're dealing with here. Is this substance? And deoxyribose is a sugar. Nucleic acid are those bases I showed. Well, it's a combination of the sugar, a phosphate, and a base. It makes what's called a nucleotide, and we're going to talk about that 2 videos from now. And a nucleotide is made up, or a whole bunch of them put together makes a nucleic acid. So that's what we've got going on there. But we'll do a lot of detail there. What I want to talk about today is kind of the pictures. You know, this is the 50s now. We're in 1952, 53, and a couple people actually took pictures of DNA. Okay, the first person to ever take a picture of DNA was a guy named Maurice Wilkins. And interestingly enough, when I was taught this part of the DNA was always taught as Wilkins and Franklin. Okay, your book doesn't even mention Wilkins, and we'll talk about why in a minute. Franklin kind of got the shaft in some of this. But the truth is, Wilkins won a Nobel Prize for his work on this, so I think it's worth mentioning his name. And here's the picture he took. Wilkins took this picture of DNA. You're like, I don't get it. Well, not a lot of people did. I mean, it's a picture of DNA, which is cool, but it doesn't give us a lot of clues about what we're looking at. Okay, and we don't really know what we're looking at. I mean, there's some guesses, but it's not a real clear picture, and that's kind of the problem with it. Even though it was cool that he took a picture of DNA, it's not understood. It didn't really help him figure out the structure. Okay, but still he did it, and he worked a lot on it. So that's what Wilkins did. Now, let me show you how they did this, because this isn't just a regular old picture. It's not like they whipped out their iPhone and took a picture of this. What they do is they start with the object. So in this case, DNA. Okay? And here they have this camera. It's not really a camera. They have this device that shoots X-rays. Maybe I should write X-rays. X-rays. Because this whole process, and I'll put it up here in a second, is called X-ray diffraction photography. Okay? So this is going to shoot X-rays. And what's it going to shoot X-rays onto? This, and then some of that's going to hit a screen here. Okay, so let's take a look here. So, pardon me. It turns out that this sucker kind of lets X-rays go through it, but it makes the X-rays bounce in a funny way, and that's diffraction. I don't know if you remember this from physics first, but here's the basic idea. So, let's take our X-ray and we shoot it, and it hits this pink line, this little pink nucleotide right here. That makes it change directions, and it comes over to here, and it makes a little mark on our screen. Okay? makes a little mark on our screen, sort of like that. Okay? Shoot another X-ray. It hits another nucleotide, bounces, and it hits like this. Puts a little mark on the screen. Okay? Kind of turns out when this hits this outer part, this blue ribbon, and that blue ribbon is a combination of a phosphate and the sugar deoxyribose, which you'll learn in a bit. But when it hits that, it still diffracts, and it's kind of up here. But the thing is, wherever it does this, this tends to hit a lot. So this area actually sort of starts to get shaded in a lot. Okay? Kind of. That. And it's got a little bit, you know, by the time this is all done, we get a little bit thinner, but it's not beautiful. But we, you know, you end up hitting kind of these different things like this. And to you and I, this means very little, right? Although I'm going to try and show you what it means. But to a trained eye, like Wilkins, you can see things there, and so this becomes a useful tool to figure out the structure of DNA. And we're going to come back to that in just a minute. Okay. So let's get rid of this for a second. Now that you kind of understand, actually, before I take this away, what I want you to understand is what they said this is like is if you had your back to a screen, or maybe you were standing back here, and this was a chandelier sitting in your house with all the little crystals on it, and you shot a light right at it, and that light hit the crystals and bounced off in all these directions on this screen that you're behind. You can't see the chandelier, but you can see the little lights. And then what you have to be able to do is you have to take all those little dots of light on the screen, and you have to turn that into a picture of what the chandelier looks like. That's what dealing with a picture like this is all about. They were trying to take this picture and figure out what this structure was, but they didn't know this. So everything that's on this drawing, they didn't know yet. So they were completely working blind on this. And I don't know if what I just said impressed you, but that's a pretty complicated feat. Okay, hang on just. Okay, so here's the deal. Here's a little history here. Now, I don't know if you remember from the video, but here's Maurice Wilkins. He works in this lab. And he goes on vacation. Holiday, they call it in Britain. I'm going on holiday. I'll see you later. Everybody's like, all right, Maurice, have a jolly good time. So he leaves. Well, meanwhile, this woman gets hired, Rosalind Franklin. She's young. She's pretty. She's considered to be kind of a rising star in X-ray crystallography. She has been recruited by this. And when I say this lab is a place called King's College. Okay, so King's College. And at King's College, she's brought in because she's a specialist on X-ray crystallography. So here's that, so you can see how that's spelled. X-ray diffraction crystallography. Now, it turns out that Maurice comes back from holiday, and he's like, oh, hello. Here, I want you to do this. And she's like, whoa, 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 whoa. You're not my boss. I was hired independently to work in this lab and do this work. And he's like, no, 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 I'm the boss. You do what I say. And she's like, no, I don't. And it turns out that these two end up having kind of a quarrel. They don't get along at all. So we'll move him over here. Okay? And it really is just a misunderstanding in a lot of ways. I mean, part of it is because she's a woman. She's not respected. She's expected to be kind of a yes person. Yes, ma'am. Yes, sir. I'll do it. You bet. She stands up for herself. She says, no, I wasn't hired as your subordinate. I was hired as your equal. And he has a little hard time with that. Okay? Well, regardless of that, she starts working by herself. And actually, she has a lab assistant named, I think, Gosling. And Gosling was what's called a graduate assistant. And he worked with her and did a lot of the work with her and experiments with her. But Wilkins is kind of in his own place, and he's doing his own work. Okay? Now, it turns out that Franklin is really good at this. And eventually, she gets this picture. And this picture becomes known as photo 51, okay? And it's Franklin's photo, and this is the picture of DNA, okay? This is the picture that allows the people that eventually figure out DNA, it allows them to figure it out. And here is who figures it out, okay? Let me move this over here. Actually, let's move it over here. These two guys, one's American, one's British. The American is James Watson, and we're going to move Maurice away. And the British one is Francis Crick. And they work together, and later they end up figuring out the structure of DNA. Turns out Watson, he doesn't get along with Rosalind Franklin either. And Crick, he's kind of in the middle. He's indifferent. He's an okay guy. But Watson and Rosalind Franklin don't get along at all. And when we talk more about Watson and Crick, I'll tell you more about their relationship. But suffice to say, they don't get along. She doesn't want to share her work like this picture with him. These guys aren't even at their lab. They're at a different lab. But she's like, I'm not sharing. I did this. I'm doing my own work. She wants to figure out the structure of DNA. That's what she's working on. Well, so she ends up taking this picture. Kind of zoom ahead in the story. It turns out Maurice takes this picture out of her desk and gives it to Watson. And then Watson takes the picture, sees it, and goes, holy crap. Doesn't say holy crap. Probably says eureka or something, or jolly good. Actually, he's American. But basically, it says holy crap, and he understands that this stuff means stuff. He's seen this. He's worked on the structure of DNA long enough that he all of a sudden can figure some stuff out. And we'll talk about what this picture means in just a second. So that's the bad part. Maurice Wilkins takes this picture, gives it to Watson. Watson uses that picture to go ahead and figure out the structure of DNA with Crick. Okay? But let's talk about what this picture really means, why it's significant. Okay? Photo 51. If we take our structure of DNA here, let me show you what we're looking at here. This is kind of cool. This blue deal right here is this. Okay? It's kind of all this outside stuff. And what we're doing is we're looking at the side of it. And I don't know if I'm going to do this credit, but I'm going to try. I'm going to get rid of that. Okay. What we're looking at really is we're looking at this kind of helix shape. So see, this goes up and then it starts to turn like that. And if we kept following it, it would turn again like this and so forth. And this side mirrors that side. And so it turns, and then eventually it turns. That's a pretty crappy helix. I think it actually goes over here, and there you go. So this part, act like it doesn't exist. So this is the helix shape. That's this. Zoom, 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 zoom. That's what these lines are, okay? And this, of course, bends down this way, and this is going to go through and bend down that way, right? And that's how we get that shape. You see that? Okay, cool. Now, see these bases here? That's what these are. And so, like, this base right here is this base. And this base right here is this base. And let's see if I can change color to help you out. The next base is that green one. And the base across from it's that green one. And what we're seeing is all these bases stacked up, and it actually turns out that if you look, you can tell that, holy crap, this is also working in a helix. Okay? It's doing the same thing. We're going up, and we're going like that, and we're working in a helix, double helix. And that's what that picture tells us, which is, to me, is crazy cool. Most people don't realize what you're looking at, but Franklin does. But she does not totally. She knows that she has some ideas, but it really, and this is the tricky part about the whole thing, it really took Watson to look at this and based on the stuff he'd done to go, oh, I know what this means. And as much as he was kind of a jerk face for taking her work, and he was, he did something incredible, and that was take her work, apply it to his work, and figure it out. But we're going to talk about the next unit. So bye, James. Bye. All right. That's why Rosalind Franklin's work is so good, okay, and so interesting. Okay, I think that's it. My last question on there is talking about how she did not win the Nobel Prize because she died. The reason she died was because she had cancer. The reason she had cancer was probably from the X-rays, these beams went out, and they ended up, I think, giving her ovarian cancer. I don't remember for sure, but it ended up killing her after the discovery of DNA. So she got to be part of that. I mean, she got to see Watson's fame, and then she died. So it's kind of tragic. That's everything about this. I hope that was helpful. I know it's a longer video. I'll try and be faster. We're almost to the end. Write up everything, and let me know if you have questions. All right, thanks. Ciao.